Hello, good evening. Any doubt from last class? Abhinav?
No doubt.
Okay. In last class, I defined you about adiabatic curve and relation with isothermal part. Let me define you some more thing. If there will be statement like quasi-static process, the process which is carried out very slow will be termed as quasi-static and will be defined for isothermal part. But if a process is carried very fast, abruptly, or all of a sudden, it will be for adiabatic process. So related to these type of process, we may define isothermal or adiabatic. Let me give you a general condition. Suppose a fully inflated balloon got burst. Will the temperature of ejecting air will be low or high as compared to surrounding temperature? First, tell me which process will be going on in this whole part, isothermal or adiabatic? Bursting of balloon, bursting of tire, whether it will be carried out at slow rate or all of a sudden. Abhinav? Whether the bursting of balloon or tire of any vehicle will be slow change or all of a sudden change?
No change, sir.
Slow change?
Sir, like the temperature will rise slowly only, no, sir?
No, I'm just asking. Bursting of balloon all of a sudden, not the ejecting of air from any pinch hole. This whole balloon
Fast
get
change.
burst all of a sudden. So you'll say it fast change, and fast change will be isothermal or adiabatic. According to the above relation, you will say fast change will be for adiabatic process. So that will become adiabatic. Now, suppose you have any balloon fully inflated like this. So will the air inside or pressure inside will be higher or lower as compared to surrounding? Let's say we have some outside pressure P0 and some inside pressure Pi. Which will be greater, Pi or P0? Atif?
Sorry, sir, can you repeat the question?
Which pressure will be higher, Pi or P0?
Sorry, PI.
Good. That's why we would require some additional work from outside to blow any balloon. It means pressure inside will be greater as compared to outside. Now, suppose this balloon got burst. So air will eject out into outer surrounding, which having some low pressure. So you'll say inside pressure is high, outside on bursting, pressure will come out to the outer surrounding, so it will become low. And since this process is adiabatic, which is taking place all of a sudden, so delta Q will be 0. At constant heat, pressure and temperature will be directly proportional to each other. Hence, temperature will become low. It means ejecting air will be colder as compared to normal surrounding air. Riba, is it clear? Abhinav? Atif, any doubt?
No, sir.
Okay, just write it down. Atif, done?
Yes.
For helium, initial state is P0, V0, expands to 8 times its initial volume. Find pressure or simply new pressure if expand isothermally or second expand adiabatically. Let me give you some hint related to this part. We have initial state of gas P0, V0, that is Pi we have P0, Vi we have V0. It expands to 8 times of its initial volume. It means V final is 8 times of V0. So we have to calculate new pressure if expansion of this particular gas in first case is isothermally, in second case as adiabatically. And we are calculating for helium gas. Helium will be monoatomic. So let me define first for isothermal. You will say we have Pi as P0, Vi as V0. Vf is given 8 times of V0. Pf we have to calculate. So for isothermal part, just use Pi Vi equals to Pf Vf, equation of state. For adiabatic process, for helium, which is monoatomic gas, so gamma will be 5/3. So just use Pi Vi to the power gamma equals to Pf Vf to the power gamma, and try to find the value of Pf in both cases. Atif, any doubt? Riba, any doubt? Okay, try to solve the value of Pf.
So can you recap? Can you explain again?
Okay. Since in this part, we have initial condition of gas P0, B0, which expands to 8 times of its initial volume. It means V final becomes 8 times of V0. So we have to calculate P final or the new pressure, okay? But this process is carried out first isothermally or second adiabatically. So for isothermal part, equation of state is P1 V1 equals to P2 V2. But for case of adiabatic, we have P1 V21 to the power gamma equals to P1 P2 V2 to the power gamma. Gamma is, since we have gas as helium, which will be monoatomic, and gamma for it will be just 5/3. Atif, is it clear?
Yes.
Try to solve PF in both cases. Atif, you have done a little mistake. Your answer is almost correct. Hiba, you got any answer? Let me solve. First, for isothermal, Pi we have P naught, Vi we have V naught, Pf we have to calculate, and Vf is 8 times V naught. So Pf, move this 8 V naught to right side, left side. So you'll get P naught V naught divided by 8 times V naught. So V naught cancel out. So you're left with P naught by 8 for this part. In second part, we have Pi as P naught, Vi V naught to the power gamma. Pf we have to calculate. Vf is 8 times V naught to the power gamma. So Pf will be P naught V naught divided by 8 times V naught, having common power gamma, that is 5 by 3. V naught cancel out. So you're left with P naught 1 by 8, which will be 1 by 2 to the power 3, further raised to 5 by 3. So power raised to power will get multiplied. So 3 into 5 by 3, 3 cancel out. So you're left with 1 by 2 to the power 5. So it will be 1 by 2 to the power 5, that will be 32. So it will become P naught by 32. Atif, is it clear? Abhinav,
Yes, sir.
Yes, sir.
any doubt?
No doubt, sir.
Okay. Just write it down.
How did you get 32?
1 by 2 to the power 5. It means 2 get multiplied 5 times. So it
Yes,
will
sir.
become 30.
Thank you. Abhinav, done? Okay. Next is work done during this process. So using first law, dq equals to du plus dw. Since dq in this part is 0, so work done will be just opposite of or just negative of internal energy. So put the value of internal energy as ncv dt, or it will be equals to minus of n r pi gamma minus 1 times dt, or further minus of p final v final minus p initial v initial divided by gamma minus 1. It will give you net work done.
Just write it down. Atif, done?
Yes, sir.
Now you'll be given graph for all different process like this, and you'll be asked to name these different process. So let me define you how to name. In first part, for a straight line which is parallel to x coordinate, so you will say in this part only volume is changing, pressure being constant, so it will be for isobaric process. The vertical line in which pressure is changing but volume remains same, so it will be isochoric. These two curves, or the curve for hyperbola related to this part, in which we have lesser stiffness for this part, so it will be for isothermal, and more stiffness in this part, so it will be for adiabatic process. Now, next question will be on the basis of work done during the entire process. So how to define work done? Work done is area under pressure versus volume curve. So if you draw this entire area, so it will be work done for this process, that is for adiabatic process. Next, work done during this part, so it will be work done during isothermal curve. And next, with this curve, it will be the total area inscribed from this point to this point. So for which curve do you think it will have maximum area enclosed within it? Reba?
Green one.
And it will be for which process? Isobaric.
Isobaric.
Then second for isothermal, third for adiabatic, and the minimum or zero for isochoric. Atif, is it clear?
Yes, sir.
So we can say work done will be maximum for isobaric, then isothermal, then adiabatic, and least in terms of isochoric, it will be 0. Just write it down. Atif, done? Okay, this is all about the whole thermodynamical process. Next is heat engine. So first, what do you mean by heat engine? So you will say an engine which convert heat energy into mechanical work done or mechanical energy. An engine or device which converts heat energy into mechanical energy. So to define this particular engine, it may consist of three main segments. First part is called source. Second part is called working tool. And third part is called sink. Source is a place or chamber where fuel burns to produce heat. So it will be termed as heat reservoir having temperature T1. So it is a chamber in which fuel burns to produce heat. So it will be also termed as heat reservoir. Second is working tool. It consists of gas with a movable piston and an enclosed vessel, which may expand or contract and supply of heat to it. So it consists of gas in a vessel with movable piston which moves to and fro related to heat supplied or ejected from it. Third is sink. It is the outermost surrounding in which excess amount of heat being ejected out. It is the place in which excess of heat being ejected out. So we call it as surrounding. Having some lower temperature T2. So this entire part, working tool will absorb Q1 amount of heat from the source, do some work to convert it, some of it into mechanical energy, and rest of it may get lost into surrounding. First, write it down to this part, then let me define you its working mechanism. Atif, any doubt related to these three different terms? Source, working tool, and sink?
No, sir.
Okay. Riba, done?
Done, sir.
Okay. Abhinav, any doubt?
No doubt, sir.
Okay. Next is working mechanism of this whole process. Suppose this is vessel of that gas with piston. This is any insulating pad. This is source at temperature T1. And this is sink at temperature T2. To define this entire process, let me explain you the graph related to this whole part. Pressure versus volume. First part, when this piston or this whole vessel is placed over source. Just assume this whole system is placed over this source. So from this source, it may absorb Q1 amount of heat at some constant temperature T1. So dq equals to du plus dw. Since in this part, temperature is constant, so internal energy will be 0. So total amount of heat supplied to the system would be utilized on changing work done only. So let's say initially A having pressure P1, temperature T1 and volume V1. So on absorbing heat Q1, it may expand to this point to reach B, pressure P2, volume V2, temperature remains T1. So it will be isothermal expansion. Atif, is it clear?
Yes, sir.
In next part, when it is reached to insulating pad, from which there will be no exchange of heat, there will be no supply or ejection of heat. So at this point, dq equals to du plus dw. Since heat in this part is 0, so sum of internal energy and work done will be 0. Now, since absorption of Q1 will leads to expansion of gas, due to which piston will go up. So in this part, it further tends to go up. So work done will increase with decrease in its internal energy without supply of heat. So we can call it as adiabatic expansion. So it may move from this point to this point, from B, P2, V2, T1 to C, P3, V3 at temperature T2 at constant heat or adiabatic expansion. Riba, is it clear?
Yes, sir.
Now in third part, when it has reached to this sink, it may have no longer to expand further more. So it will eject some Q2 amount of heat into surrounding or sink at some constant temperature T2. So it will start contracting from this point to this point, C having P3, V3 temperature T2 to D, P4, V4 remain temperature T2. This will be isothermal contraction. dq equals to du plus dw. Since in this part temperature is constant, so du will be 0. So amount of heat ejected out from this particular system will be equals to compression of this gas. In last part, it will go from D to A, P1, V1, temperature T1, from P4, V4, temperature T2, adiabatic compression to acquire its initial state. So dq equals to du plus dw. Since there is no supply or rejection of heat in this part, but piston is compressing down, so work done will decrease so that internal energy will increase to acquire initial condition of gas. So this is the entire mechanism of heat engine. So you'll say it will have 2 expansion and 2 compression, 2 isothermal and 2 adiabatic curve. Atif, any doubt?
No, sir.
Okay, just draw this. Atif, done?
1 minute, sir. Done, sir.
Okay. So related to this entire part, we have to calculate net work done during this whole process. So net work done will be work done along A to B, work done along B to C, C to D and D to A. Along B to C, that is adiabatic expansion, will be just equal and opposite to adiabatic compression over D to A. So these two will cancel out. So work done along A to B will be equals to amount of heat supplied to the system. So it will be Q1. Along C to D, it will be heat ejected out from the system. So it will be Q2 with negative sign. It means net work done during this entire process will be Q1 minus Q2. Now, related to this part, we have to calculate efficiency or working ability of performance of this heat engine. So next is efficiency. Eta is equals to work done, that is how much it has ability to convert into mechanical energy to the total amount of heat supplied or given to it. So it will be heat absorbed. Work done is Q1 minus Q2. Heat absorbed during this process is Q1. So further, it will be 1 minus Q2 by Q1. So this is efficiency in terms of Q2 and Q1. Next, you will be asked to calculate this efficiency in terms of temperature. So let me define you how to convert this expression in terms of temperature. As Q2 is amount of heat ejected out from the system at constant temperature. So it will be NR temperature T2 ln V final by V initial. I've just written this from C to D. At point C, we have volume V3. At point D, we have volume V4. And this process is an isothermal process or isothermal compression. So total amount of work will be equals to heat. So work done will be heat equals to nRT ln V final by V initial. And Q1 equals to nRT ln V2 by V1 for A to B. Since work or heat supplied to the system will be taken as positive, so it will be positive, and heat being ejected out from the system, it will be taken as negative. Heat supplied to the system will be taken as positive. Heat ejected out from system will be taken as negative. I have just used this signed convention. Atif, any doubt?
No, sir.
So on dividing, you will get Q2 by Q1 with negative sign equals to NR gets cancelled out. So T2 by T1 ln V4 by V3 divided by ln V2 by V1. So we have to somehow relate these two parts, so it will become cancel out, and we're left with just T2 by T1 equals to Q2 by Q1. First, write it down till this, then I'm proving the rest part. Abhinav, done?
Yes, sir.
Okay. Now, for B to C, that is for adiabatic expansion, at point B, we have temperature T2, volume. At point B, we have temperature T1, volume B2 to the power gamma minus 1 equals to, at point C, temperature T2, volume V3 to the power gamma minus 1. Move this T2 to left side, so you will get T2 over T1 over T2 equals to V3 over V2, having common power gamma minus 1. Now, if you move this exponential to other side, it may get reciprocal. So it will be T1 minus T2 to the power 1 over gamma minus 1 equals to V3 by V2. So this is first expression in terms of temperature. Next, similarly, for D to A, at point D, we have temperature T2, volume V4 to the power gamma minus 1. I'm using adiabatic equation of state for temperature and volume. At point A, T1, volume V1 to the power gamma minus 1. Now move this T2 to right side and V1 to left side. So you get V1 by V4 by V1 to the power gamma minus 1 equals to T1 by T2. Now move this exponential to right side. So V4 by V1 equals to T1 over T2 whole to the power 1 over gamma minus 1. Now just compare these two equations. We have same quantity temperature for both these two expressions. Atif, is it clear? So we can equate these two terms. So we can write V3 by V2 equals to V4 by V1. Just move V2 to other side and V4 to other side. So you'll get V3 divided by V4 equals to V2 divided by V1. First, write it down to this part. I'm using this relationship.
Done, sir.
Okay, so now since we have Q2 by Q1 equals to T2 by T1 multiplied by ln V4 by V3 whole divided by ln V2 by V1. So in numerator, if you reverse the fraction, there will negative sign with it. But let me give you a property. If you have minus of ln x over y, this minus will reach to its exponential like this, x over y to the power -1, and this -1 will change numerator and denominator, so it will become y over x. So I'm using this part. So in numerator we have v4 by v3. So if you reverse it, they will have negative sign. So minus of T2 ln V3 by V4 divided by T1 ln V2 by V1. According to the above relation, we may write it as V3 by V4. Since V3 by V4 equals to V2 by V1. Atif, is it clear?
Yes, sir.
Now, ln part will get cancelled out, minus minus will cancel out. So you're left with Q2 by Q1 equals to T2 by T1. Therefore, eta equals to 1 minus Q2 over Q1. It should be equals to 1 minus T2 over T1. Riba, any doubt?
No, sir.
Just write it down. Abhinav, done?
Yes, sir.
Now, related to this part, you'll be asked whether it will be possible to construct heat engine having efficiency 1 or 100%. So you will say, if efficiency of this particular heat engine going to be 1, it means T2 in that case will be 0. T2 will be 0, it means T2 is 0 Kelvin. And for 0 Kelvin, in last chapter I defined you, there will be no existence of matter. It means it won't be possible. Hence you can say efficiency of heat engine can never equals to 1 or unity. So for eta to be unity or 1, T2 must equals to 0 Kelvin, and at 0 Kelvin, no matter can exist. Hence, it won't be possible. Atif, any doubt?
No, sir.
Now, related to this part, let me give you a question. Find efficiency of heat engine working between 27 degrees Celsius and 127 degrees Celsius. If it absorbs 2 kilojoule from source, find work done and heat ejected. Just use the above formula and try to find these terms. First, try to convert each temperature into Kelvin, then use the formula for efficiency to find rest of the thing. Try to solve. Atif, take the higher temperature to be temperature of source. That is T1 we have 127 plus 273. So it will become 400 Kelvin. And T1, that is lower temperature, 273 plus 27, that is 300. So use this and try to find eta. Good, Atif. We have heat absorbed from source is 2 kilojoule. That is Q1 is 2000 joule. Try to find work done and heat ejected. If you want to calculate efficiency, it will be eta equals to 1 minus T2 by T1. 1 minus T2 we have 300 Kelvin, T1 we have 400 Kelvin. 0, 0 cancel out, 4 minus 3, that will be 1 by 4 or just 0.25. It absorbs 2000 joule from source. So again, eta equals to work done by heat absorbed. So work done would be eta, that is 1 by 4 times Q1, 2000. So it will be 500 joule. And work done equals to Q1 minus Q2. So Q2 will be equals to work done, Q1 minus work done. So it will be 2000 minus 500, that is 1500 joule. Riba, is it clear?
Yes.
Abhinav, any doubt?
No doubt, sir.
Okay. You all have written till this?
Yes, sir.
Okay. Next is, there will be some limitation of first law. First law simply states flow of heat will be unidirectional, that is from higher temperature to lower temperature, and reverse will not be possible. So you will say first law defines unidirectional flow of heat, that is from higher temperature body to lower temperature, and reverse is not possible. So on the basis of which let me define you statement related to second law. For second law, there will be two different statements. First is Kelvin Planck statement, and second is Clausius statement. For Kelvin Planck state, suppose you have a source working tool and sink. It absorbs heat from source and convert the entire amount of heat into work done. It means there is no any loss of energy into surrounding or in sink. So according to Kelvin's statement, it states no process is possible whose sole result is absorption of heat from source and conversion of entire heat into mechanical energy or work done without any loss in surrounding. It means in this case, efficiency of heat engine will become unity or one, it won't be possible. In second part, for Clausius statement, it state, suppose this is body which is at higher temperature, working tool, body at lower temperature. So it state it absorbs some Q without giving heat or work from outside. It ejects Q to higher temperature. So there will be no process whose sole result is transfer of heat from lower temperature to higher temperature. It won't be possible. Atif, is it clear? These two statements?
Yes.
Okay, first write it down till this part, then I'm defining you the statement. Atif, done?
Yes.
So in first part for Kelvin statement says no process is possible whose sole result is absorption of heat from source and conversion into mechanical energy, that is work done without any loss. In second part for Clausius statement says no process is possible whose sole result is transfer of heat from lower temperature body to higher. So on conclusion, we can say to flow heat from some lower temperature body to higher temperature body, you must require some external agency to do some work. So we can say no heat can transfer from lower temperature to higher until work or external work is done. It means external work or external agency is required to move heat from lower temperature body to higher temperature body, unless it won't be possible. So on the basis of this statement, let me define you working of fridge or refrigerator and heat pump. Just write it down to this. Riba, any doubt? Abhinav, done? Okay, Next is, on the basis of this second law, we define refrigerator and heat pump. In first part, this is Kelvin, that is a region of interest. At some lower temperature T2. So it absorbs smaller amount of heat from some lower temperature Kelvin by adding work from compressor. It ejects higher amount of heat into surrounding. During this process, it will be capable of lowering the temperature of Kelvin so that it may start cooling down. So refrigerator has to eject out heat from Kelvin to cool it down. Similarly, for heat pump, it extracts heat from surrounding at low temperature Q2 during winter by adding work from compressor. It ejects higher amount of energy or heat at temperature T1 into a room, which we have to, or for which it has to warm up. So we can say it is a region of interest. So both has same working ability or between same term, but due to change in its region of interest, working performance will be different. So in first part for fridge, we can say it absorbs heat from Kelvin by adding work of compressor. It ejects heat into surrounding. So working performance of this fridge in this condition, working performance. In case of fridge, how much it has the extract heat Q2, how much energy is utilized or given to this particular fridge from electricity or from through compressor, it will be work done. So heat absorbed from cabin divided by work done by compressor is called its working performance. It is denoted by alpha. Heat absorbed is Q2. Work done will be Q1 minus Q2. In terms of temperature, it will be T2 divided by T1 minus T2. Atif, any doubt?
So,
Similarly, in case of heat pump, we may define it absorbs heat from surrounding at low temperature by adding work of compressor. It donate higher amount of heat into room to warm it up. So working performance related to this part will be amount of heat donated into a room divided by work done by compressor. It is denoted by beta equals to heat donated Q1, work done Q1 minus Q2. So it will be equals to T1 by T1 minus T2. Now we have defined three different engine. First is heat engine, second is fridge, and third is heat pump. So there is relation in between these three different terms. Beta is equals to alpha plus 1 equals to 1 by eta. So just remember this particular relation in between these three different terms. Write it down from this part. Atif, written?
Yes, sir.
Any doubt related to this whole part?
No, sir.
Okay. Now, there will be one conceptual question related to this. You will be asked, what will happen to the temperature of the room if door of fridge is kept open? Atif, will the temperature of room will increase or decrease? Riba, suppose you have any enclosed room in which a fridge is placed whose door is kept open like this. So what will happen to the temperature of room? Will it increase or decrease? Just think the working of fridge. If you kept the door open, cabin and whole room will act as single system. So it extracts some small amount of heat from cabin or from surrounding. By adding work of compressor, it ejects some larger amount of heat into same room. So on each cycle or in each cycle, work of temperature will tend to increase the temperature of this entire room. Hence, the temperature of room gradually increases. Atif, is it clear? Riba, any doubt? We can say in this part, if door of fridge is kept open, then cabin and whole room become common. So it absorbs lesser amount of heat Q2, and by adding work of compressor, it donates larger amount of heat Q1 into same room. Hence, temperature of room will gradually increases. Atif, is it clear?
Yes, sir.
Okay, just write it down. Atif, done?
Yes, sir.
Okay, so this is the entire part of this whole chapter. So we have just finished it. So let's stop here for today. In next class, we'll start new chapter, that is kinetic theory of gas. Okay.
So what is the chapter?